So in this unit, our primary focus is going to be looking at how we can apply integral calculus to myriad scenarios, just as the way in Unit 3 we looked at how we could apply differential calculus to myriad scenarios. So the first main application that we're going to look at is how we can use calculus to determine the average value of a function over a certain interval, the same way that we use statistics to determine the average value of a data set. 6.1. So, deriving the average value of a function over an interval is a very useful tool, especially in probability, where we're given a very, very large data set to the point that it's better to model the data set as a function than as a list of discrete numbers. Okay, so we're going to look at how we can go from the average value of its discrete number, list of discrete numbers, something that we see in Algebra 2, and promote that and upgrade that to the average value of a function, which again we can use that function in probability and higher level probability in order to determine the average value of a specific type of probability distribution. Okay, so let's start off with an average value of a set of numbers yi, where yi denotes the ith number of our set. Okay, how we would get the average is we'd take the sum of all numbers in this set and we divide it by the amount of numbers or the quantity of numbers that we have in this set. Okay, something that we all should know from Algebra 2. So in this case, we can write our sum as sigma starting at I equals 1 to the nth number, where n is again the quantity of numbers we have in our list, of yi, where again yi is the ith number in our list. So we're adding together all of these numbers. And then we're dividing by the quantity of numbers we have in the list, n. So suppose that yi actually denotes the ith y value of a function f at a specific x value x sub I. Okay, so yi is equal to the value of a function f at xi. So in this case right here, all right, all these y values that we're using to get an average, all right, we can now look in terms of a Riemann sum. Okay? So what we've done right here is we've taken all of our y values, f of x1, f of x2, f of x3, aka y1, y2, y3, y4, so on and so forth, and we fitted a curve to these y values here. So next thing that we're going to do is we're going to calculate the distance between each y value, aka f of x1, f of x2, and this distance is going to be delta x, okay, the distance between the successive x values. So delta x again is going to be b minus a divided by n, where b and a are going to be, where a and b are going to be the first and last set of numbers, or the first and last numbers in our set of numbers here. So a and b are the first and last numbers in this set. So delta x then is going to be b minus a divided by n, the quantity of numbers that we have in our set. So what we can do right here is we can solve this equation right here for 1 over n, which in this case means we're going to divide both sides by b minus a. So we're going to get 1 over n equals delta x divided by b minus a. Okay? And why are we doing this? Well, we're going to see in a second. Okay? So what we're going to do is we're going to replace 1 over n in our equation, in the average equation. Okay, so notice how we have a division by n right here in our average equation, and we're going to replace this with delta x over b minus a. So as a result, we're going to get we're going to get that the average equation, by replacing 1 over n with delta x over b minus a, can be turned into the summation of f of xi times delta x divided by b minus a. We replace yi with f of xi, and we replace 1 over n with delta x over b minus a. So this is the equation that we arrived to so far for our average value. It looks pretty ugly right now, but it's going to condense down to a very nice result on the next slide. So what we can take note of right here is that if we let the quantity of numbers n that we have in our data list go to infinity, aka we have an infinite amount of numbers in our data list, okay, what we're going to have is going to have a limit of Riemann sums, okay, so the limit as n goes to positive infinity, which if you recall from Unit 4 is how we used to define the definite integral, okay. So as a result, we can see that the average value of a function f over an interval ab, what we'll denote as av of f, is going to be equal to the definite integral from a to x equals a to x equals b of f of x divided by b minus a. So in this way right here, if n becomes an infinite number, meaning we have an infinite amount of data points in our set, it's going to be impossible to find the average sum by adding all of those y values together. So what we can do is approximate those y values to a function like we've done right here, and then we can calculate that average value of the function over that specific interval using a definite integral divided by b minus a, the size of our interval. So this equation right here always holds and will give you the average value for any specific function f over a specific interval a to b. So there are some connections between the average value of our function f and the average rate of change of its antiderivative, capital F. Okay? So specifically, okay, what's interesting about this equation we've just found is that it equates the average value of f over an interval with the average rate of change of its antiderivative, capital F, over the same interval. The reason being is that from the first fundamental theorem of calculus, we have that our definite integral of f from x equals a, x equals b is equal to the change in the antiderivative over that same integral. So as a result, we can replace this definite integral right here in our numerator with the change in the antiderivative from x equals a to x equals b. So we have the change in our antiderivative from x equals a to x equals b divided by b minus a, which is going to give us average rate of change of our antiderivative over this interval. So the average value of a function f is always going to be equal, over an interval is always going to be equal to the average rate of change of its antiderivative, capital letter F, over that interval. Okay? So physical interpretation that we can use to think of this last result on our last slide right here, in order to put it on better footing, is that we can think of average velocity can be calculated as the average rate of change of position, like we saw back in Unit 3. Average velocity equals average change in position divided by time. So x of t2 minus x of t1 divided by t2 minus t1. Or the other way that we could calculate our average velocity is it could be calculated as the average value of the velocity function over an interval. Meaning we can take the integral of our velocity function over t1 and t2 and divide that by t2 minus t1. So we can see that both of these equations are the same. So we can see that the average rate of change of the velocity function is going to be equal to the average rate of change of the position function, where position is going to be the antiderivative of velocity, since velocity is the derivative of position. So let's look at an example of how this looks in practice and how we can use to determine and see if this is correct right here. So what is the average value for x plus 6 over the interval x equals 0, x equals 4? So we can take note of right here is that 4x plus 6 is the equation of a line. Okay, so at x equals 0, our line is at y value of 6, and at x equals 4, our line is at a y value of 22. So because this is the equation of line, we would expect that the average value for x plus 6 over this interval would be at the midpoint y value between y equals 6 and y equals 22, which is going to be y equals 14. So we should expect to get an average value of 14 here. Okay? So what we're going to do is we apply the average value equation. We have the average value of f over this interval is equal to 1 over 4 minus 0 multiplied by the definite integral of from x equals 0 to x equals 4 of 4x plus 6. So as a result, we're going to have 1 over 4, definite integral from 0 to 4 of 4x plus 6, or 1 over 4 equals 2x squared plus 6x, evaluated from x equals 0 to x equals 4. So that's going to give us as a result 1/4 times 2 plus 4 squared plus 6 times 4 minus 0, which is going to give us 1/4 plus 32 plus 24, which is going to give us 14. Confirming our prediction as we would expect.